Okay, so we're moving away from bivariate scatter plots and making predictions and things and moving into inference. So the material that we covered before this was all in chapter 3. Now we're up to chapter 12. And we're going to be looking at inference for regression. So let's jump in and see what we've got here. Okay, so what we're going to be doing is going back to tests of significance and confidence intervals. So we're going to test claims and we're going to do some estimation, and we're going to work off of least squares regression lines or least squares regression equations. And it's really kind of a form of inference that you don't see very much. I've never seen it outside of this course. But the AP folks, the College Board wants this covered. By golly, we're going to cover it. So we're really going to concentrate specifically on the slope of the least squares regression line, because if we can show that we do have a slope that is different from 0, then we're going to show that we have a linear relationship. If, however, we don't see any difference from a slope of 0, that is not a linear relationship, okay? So that's sort of where the whole thing is going, but we're not going to be doing the tests of significance today. We're not going to be doing the confidence intervals today. We're going to be looking at more of the setup. So here goes with that. So the preliminary checks are that if we have bivariate data, we need to graph it, put it in a scatter plot, and make sure we're comfortable with it being a linear relationship. So we're going to construct and plot the LSRL using a TI calculator. And once we've done that, we can do things like, get A, get B, get the slope and y-intercept of our model, look at residuals, just make predictions, do all manner of things. So running a least squares regression is pretty important in the process. We're going to look for outliers and influential observations, because we know that inference is really a tough deal when we have outliers. We had problems with t-tests, small sample t-tests for means always suffered if we found outliers. That was a violation of assumptions. So if we have outliers, remember those are displaced in a vertical direction. Influentials are displaced in a more horizontal direction. If we see those, then inference is not safe. Okay, and again, residual plots, we're going to be looking over them. So look, y hat equals a plus bx is a model that we've been working with that we get through sampling. And it provides us with a slope for our LSRL and a y-intercept, and that's a for the y-intercept, b for the slope. Now those are always lowercase, and they're regular letters that we use, non-Greek, because they come from a sample. But what if we could, instead of just grab a few individuals and get an ordered pair from them and make a scatter plot, what if instead of doing that, we could get everyone, the whole population, to provide us with ordered pair data, bivariate data, and then we could make a big, gigantic, busy scatter plot out of that. Then we would get a true least squares regression line from that. And those are going to replace A, your y-intercept, from a sample with alpha, which is a recycled Greek letter. We've used it for other things. And that would be the true y-intercept for an LSRL from the entire population. Likewise, B is the slope from a sample. If we could get a true slope from a population, it would provide us with beta. So A and B are statistics, alpha and beta are parameters. And we're going to use A and B to estimate alpha and beta. So somewhere there is a true average linear model, which would then be mu sub y equals alpha plus beta times x. This is an unknowable equation, just like any parameters are, but it's there somewhere, and we can try to do our normal workarounds to get some idea of what it might be. All right, so assumptions. Whether we're doing linear regression, confidence intervals, or linear regression t-tests, we have to meet these assumptions. First of all, we have to have a straight line relationship with x. We would never know that, given that, mu sub y is a parameter. But if we look at a scatter plot from data, we can infer back. So if we see a straight line relationship in a scatter plot, we can verify this assumption. All right, for every value of x, y must vary according to a normal distribution. Now that's a weird one, okay? That's even hard to picture. So here's a graphic. All right, you can tell that this was built from the population because it's got parameters, and there's an LSRL through it. So I guess we decided that it is a linear model. And if you look at it, like here is a normal curve for a specific x value. So for this x value right about here, all the y's that are spread around this LSRL are spread in a normal way. And so this x that is producing this scatter plot, I'm sorry, this distribution for the y's at this x, these are also normally distributed. And this x produces y's that are also normally distributed. Okay, basically any x should produce a normally distributed assortment or distribution of y's. And so this thing would suddenly have so many little normal curves that it would make kind of a three-dimensional solid that would look like a bread box or a tunnel, something like that. So this is what we're talking about. We pick an x, like maybe up here. All of the y values that are at that x would be normally distributed. Yeah, that's a little hard for us to verify, but we will be able to, and I'll show you how in a minute. All right, so normality. All right, we examine subsamples at different values of x, make histograms like at this. Here's a histogram. All right, there's a lot of detail there, but it's sort of mound-shaped, okay? So this is good. This, on the other hand, if we were to check another slice out of here and we got something bimodal like this, nah, that would not be very good. I know what you're thinking. Do we have to take a scatter plot and just like take slices out of all of it and check this? And the answer would be no. We've got quicker ways than that. All right, so more assumptions. We have two. Now there's a third one. Y values are independent of each other. Okay? We'll talk about how to verify that. Okay, here's another one that's harder to verify, like the one, the second one on the previous slide. Now the standard deviation, or the spread of the y's, is the same for all values of x, and y, that standard deviation is sigma. Okay, same for all values of x. This means that the spread of the y's for all values of x are the same. Here's that same graphic. And all that we're saying here is that if we could fill this in with all the normal curves that would, represent the distributions of y at all the x's, again, it would form a bread box or a tunnel, but that bread box would be consistently spread out, or the tunnel would. It won't pinch in anywhere. It won't stretch out anywhere. It's going to be, let's say the tunnel has a width of 25 feet. At the base, it would be that way all the way through. Okay, it would be consistent. All of these would be the same standard deviation all the way from beginning to end in this population scatter plot. Again, you're thinking, how can I possibly, check that assumption? All right, let's just hold off on that. So equal error variance, okay? Error being the spread around the LSRL, okay? If you look at this, and we just kind of take little bitty slices, see how they're roughly the same length? Okay, right, so this is a little longer here and a little shorter here and whatnot, but roughly they're about the same. All right, this looks pretty good. All right. Oh, by the way, let's go back and pronounce this. Let's go back. This is homoscedasticity, and that just means equal spread throughout a scatter plot for the y's. Remember, y's are vertical. And this is a term you don't have to know. It's something I learned when I was in college, and I think it's cool to say it. So we're seeing homoscedasticity, right? Homo meaning the same. This is heteroscedasticity, and you can just tell by looking at it where the difference is. If I put a slice here, it's going to be a big slice. As I get further and further and further and further to the left, those slices get smaller and smaller, right? So at higher values of x, error variance increases a lot, and it's not very prevalent down at the lower values of x. So this is unequal error variance. This would be a violation of assumption. This looks pretty bad, okay? Heteroscedasticity. So how do we check them? All right, linear, that first one, we have to be in a linear setting. Scatter plot looks reasonably linear. That's easy. We just make a scatter plot. And does it fit a linear model well? Well, we're used to making that decision, so that shouldn't be very hard. All right, equal variance. Just check your residual plot. If it has sort of a constant spread, like it won't trumpet out to either side, then we have equal variance. All right, the normality. What we can do here is construct a normal probability plot of residuals. And if it lines up, you know how residual plots always line up to a slanted line? If it lines up pretty well, then we have approximately a normal sampling distribution. Yay! Independence. This is where measurements for y for one subject doesn't have any bearing on those from any other subjects. The best thing we can do about this is if we have a simple random sample, that will cover the independence. I think we had that for chi-square as well. So this is these are easy to check, not hard to check. So know these assumptions, know them. All right, these are things that you might have to list and verify. They might have to show up in like multiple choice questions, you know, things like that. Okay, so if you meet assumptions, then we use the least squares regression line to have b, the slope, in that, you know, from the sample, is an unbiased estimator of beta, the true population slope. A, the y-intercept from the sample, is an unbiased estimator of alpha, the y-intercept from the entire population. And now this is the new one, all right? We're going to have to spend a little bit of time on this. All right, S is the standard deviation of the y's, and that if that's you know, consistent throughout the scatter plot, then it's an unbiased estimator of sigma, the true population value. Okay. Do you remember when we calculated standard deviation of a data set, and we said that it was the average of the spread of the values around the mean in a, you know, univariate data set? Okay, here it's almost the same thing. It's the average of the spreads of the y values about the least squares regression line. So instead of, you know, the mean in a univariate, it's the LSRL in a bivariate. And they'll both have S's, and they both replace sigma, okay? Other people will say that S is the average of the residuals, or the error about the LSRL. And so long as it's consistent through the scatter plot, we're gold. Now the calculator will give all of these values, but in case you're wondering, here's the formula for calculating that value of S, the standard deviation of the y's. And if you look at it, here are, remember, it was deviations, you know, that we squared so that we didn't have them cancel out. Then we added them up. Then we averaged them. Only for a univariate, it was 1 over n minus 1 for degrees of freedom. Here it's 1 over n minus 2 degrees of freedom, which we'll talk about. All of this under the radical is variance. Take the square root, and it's standard deviation. So it's the standard deviation of the error. Y minus y hat is error. So there it is. So more about it. It's called the standard error about the LSRL. We used the n minus 2 for n minus 2 degrees of freedom in the formula. It's because it's a bivariate setting. So there's n minus 1 degrees of freedom for x, n minus 1 degrees of freedom for y. Altogether, that's n minus 2. So that makes sense. Remember that, because in inference for linear regression t intervals or t tests, you might get asked what the degrees of freedom are. Just check what the number of ordered pairs is and just subtract 2 from it. So if it's built with 26 ordered pairs, it has 24 degrees of freedom. Okay, so we're going to use this example in order to check assumptions. So I'm going to get out of here, and I do have this already stored up in my calculator. So there it is. All right, this is something that we've used before, and let's go ahead and just run through these assumptions really quickly. All right, so the first one, we've got to check the scatter plot to see if we have a linear model. All right, so let's just go ahead and get out of here and come over here. All right, we're going to add a variable. We're using cry count of a small kid to predict IQ. All right, now I'm not asking you to tell me, is that a strong linear model? Because clearly it isn't. This is not a strong linear model. But is it linear as opposed to curved? And I would hazard a guess that yes, this is, I would call this positive, linear, and weak. Because it's pretty circular here. I mean, it's got a few points that kind of grab you and line you up in a positive direction, but it's pretty weak. But it is linear, and it is positive, okay? All right, so the next thing we need to do is to run the regression, all right, which I think I've got a clear thing here, and then I'll be able to get some residuals out of it. All right, so statistics and stat calc and linear regression a plus bx. All right, we're using crying to predict IQ, and that's going to be where we're storing things. I mean, I can change that and just make it F1. And let's go down and have it do its thing. So go down and hit OK. Okay, here's your A, which is your estimate of alpha. Here's your B, your slope, which is your estimate for beta, y-intercept, and slope. Here's R, which is pretty weak. And only about 21% of the variation in the IQ can be explained by the variation in the cry count, so it's weak, all right? But it did make the residual, so we can come back here and we can change this to stat resid. Yay. All right, this might be a little bit of an interference with our inference, because it's a little offset, but in general, I think we're okay that the spread is fairly random all throughout here. I mean, it goes up a little high here and it goes down a little low here. But in general, I would say, given that it's raw data, that we can live with this and we can call equal variance. All right. So let's check the normal probability plot of the residuals. And that's going to be pretty cool. All right. So what we can do is come back and we can make another graph, and we can go ahead and just put in stat resid. All right, and then we don't need a y because these are now univariate. All we're looking at is one variable, and that's your residuals. And we can come in here and change the plot to normal probability plot. Ooh, that lines up really well, right? That lines up beautifully, okay? And so we can go ahead and say that we have normality of the sampling distribution. Isn't that neat? So the only other thing is the independence, and we didn't get to see what exactly was involved with picking the sample. Let's assume, since it's from a study, that it is good, all right? It is from a sample, okay, that was picked randomly. So we're good. we saw linear behavior in the scatter plot. We had arguably an okay amount of equal variance in the residual plot. We're seeing normality here, and we'll just assume independence because we're assuming that the sample of these kids was picked randomly. Now I'm going to do one other thing, and this is going to be a little bit outside of what we're dealing with, and I can't seem to find what I'm looking for here, so let me see if it's hidden away here. I'm looking for this. Okay. What I want to do here is show you a little bit of a window into tomorrow, okay? So what I'm going to do here is run a linear regression t-test. I'm not going to tell you what it's all about, and I'm not going to tell you how to interpret it. I'm just going to run it so that we can see some of the values it produces, right? So I'm going to go to stat test, and here's a linear regression t-test right here at choice A. So I'm going to pick it, and remember I'm doing crying to predict IQ. I'm going to save it to F2, why not, all right? And it doesn't really matter what my alternative is. You can just leave it at not equal to. Sometimes it'll be that, sometimes it'll be directional, but let's just leave it there because I'm not really running a test today. Okay, so this is what we get when we do that. All right, we get a t-value and a p-value, which we'll deal with tomorrow. We get the degrees of freedom, useful. We get the y-intercept, useful. We get the slope, useful. There's that s value, see it? All right, that's important. That is the standard deviation of the y values, right? So we need that. This we'll need. This is the standard error of the slope. We need that more tomorrow. Here's the same r and the same r squared, and even produce residuals. So you might make an argument that running this linear regression t-test is actually more revealing than just running a straight linear regression. So keep that under your hat. Maybe run it once or twice just to make sure, and you can grab whatever you need out of this linear regression t-test. Pretty neat, okay? So I'm going to close that down and come back to the PowerPoint. Okay. So let's see. We kind of checked all the assumptions here, and we ran through the process here. We did all of the things we needed to do, so I'm not going to read them over again. And don't forget computer output. And this should help us because we've already seen all of this practically, okay? Here is the LSRL in context, right? This constant has to be the y-intercept, right? Because that is the only constant that's here. There it is. And the cry count is going to be what's the slope. That's here. Here is that S value, which is a little rounded up from what we had, but it's exactly the same thing. Remember, we can get the correlation out of here by just taking the square root and keeping it positive because your slope is also positive. There's that standard error of B that we needed. Has the same t and p value. You don't need these top three things that it says we usually ignore in this little pill region right here, okay? So we're really gold. All we need to do is understand what it is we're looking for in inference and write it up properly and draw good conclusions and maybe look at a few relationships that are present in the process, okay? All right, so the homework is worksheet number 1, and hey, that's everything I've got. So, ask questions if you need to, and we're going to wrap up the year tomorrow with inference for linear regression. So, have a good night, and on that note, thanks for watching.